Let's do. Well, what would it force be? Would be m and some acceleration, right? Or it would be force of gravity, right? The mass times accelerating the gravity.
How old are you?
By the way, I'd like to say, say that. Yeah.
All right, page 7 in your packet, guys.
Actually, this is a not bad. And then if it asks to find the acceleration, then you would do 4f equals mx together, right? M cancel, it's A equals 4. And then you could
All right, page 7. Let me just go through the notes and then we can use the second half of class to continue reviewing for your test tomorrow. So today we're talking about Taylor polynomials. So Taylor polynomials are created to help us approximate other functions. And what I mean by other functions are other families of functions like sine, cosine, natural log, rational functions, exponential functions. Okay. And so why would we do this? Why would we want to use polynomials to approximate other functions? Well, because polynomials are easy to work with in calculus. It's easy to find a derivative. It's easy to find an integral. It's predictable. Meanwhile, natural log and these other functions tend to not be as clean in terms of the derivative and integral, especially if you're trying to find the 5th, 6th, 7th derivative. It's a lot easier. Polynomials are a lot easier to manage and to work with. So our goal, well, what I want to show you is that that we can use polynomials to not only mimic these functions, but it can create exact replicas of these functions, basically using these infinite series. Once we find that pattern, we use infinite series to get that to get these polynomials to take the shape of these other non-polynomial functions. Okay, so a Maclaurin polynomial is a special type of Taylor polynomial. This is where it's centered at 0. What that means is the polynomial is going to start building its, or it's going to start mimicking the graph starting at 0. It's going to start from 0 and it's going to start building out. So, so the center just means the starting point where it begins to build copying, where it begins copying the other function. So to start, we choose an x value to center our polynomial. Sorry, a Maclaurin polynomial, it starts at 0, but a Taylor polynomial can start at 0, but could also start at other x values. Could start at 2, could begin its copying process at -2. So Maclaurin polynomial is just a special case that starts at 0. So to start, we choose an x value to center our polynomial approximation. Let's call that x equals c. So it doesn't have to be 0, it can be c. So let's say we start off here. Okay, just some random point. Our approximation will have the same y value as the original function x equals c. So f of c is equal to p of c. So the first step in copying a graph is finding that order pair that is shared. So we're going to at least have the order pair filled out the same. and then we can start mimicking the other properties of the function. The slope at that point, the concavity at that point, and then third, fourth, fifth derivative, so on and so forth. We expand the approximation about x equals c. Another way to saying this is that the function is centered at x equals c. So let's look at an example here. Explore an example with f of x equals e to the x. Let c is equal to 0. So we know that f of 0 is equal to e to the 0, which is 1. So that's, we have to, I mean, if we want to get a polynomial to mimic this exponential function, it's got to at least share the same order pair at that point. So the order pair is 0, 1. So got to have that information. We also want to make the graphs have a similar shape at that point. And so the next thing is, well, they have to share the same slope, right? It's got to have the same slope as the curve at that point. So we can find f prime of x is equal to e to the x, and f prime of 0 is going to be e to the 0, also 1. So that means, so now what we want f prime of 0 to equal to the slope of the polynomial that we're building, p prime of 0. So if our order pair is 0, 1, and if our slope is 1, our tangent line equation is y minus 1 is equal to 1 times x minus 0. Y is equal to 1x plus 1. Maybe something like this. Okay, that's great that this equation has the same slope and the same point as the curve, but it doesn't really look like the curve, right? I mean, yes, it's got the same point and same slope, and if I choose points around that tangent line, at least I'm going to get something close to my curve, but that's only a tangent line approximation. It's not doing a very good job of matching with this curve. It doesn't look like the curve at all, except at that point. So we call this a first order approximation. It's not a very good approximation, but it does two things. It at least gets the point right, at least it gets the slope right. It works for a very small interval around the point of center. So to improve the approximation, or to improve our polynomial, what if we were to make it agree with the curve, the same concavity, the same third derivative, the same fourth derivative, the same fifth derivative? And I just want to show you visually what a polynomial can do the more information we give it. Okay, so don't have to write this down. I just want to show you on Desmos what a polynomial that matches derivatives of the original function beyond the first derivative or beyond slope. Let me find that. Give me a second. Share the screen here. Okay, so this is e to the x, right? That's the function e to the x. So this is a first order Taylor polynomial, right? Not very good, right? Just y equals 1 plus x. But what if we can get this graph to also share the same concavity, or sorry, the same concavity as this curve at that point? Then the graph will look more like this, right? Doing a better job, right? It's at least curving in the same direction. Obviously, as we get further and further away, it's going to take a lot of work for this graph to eventually look like this. But I just want to show you the improvement as we give it more information. Like, what if we were able to get the third derivative to match with that of e to the x? Then the graph will look like this, right? I mean, it's doing a pretty good job on the right side. Even as we move to 5, it's pretty close, right? but this is only this is only a third degree Taylor polynomial. Okay, let's look at the fourth degree Taylor polynomial. Right. I mean, the left side is going to take a lot of work, but you see the right side, it's matching better and better with the shape of e to the x. Right, and then this is the fifth degree Taylor polynomial. How many did I do? This is sixth degree here. Okay. So it's going to keep kind of going from an even to an odd function, and as it gets more information, if it goes out, if we can follow this pattern out to infinity, the idea is that this graph will eventually look like this e to the x graph. I mean, it's doing a better job on the right side, but the left side is going to take a lot of work. But that's the idea, is that not only can we get a polynomial to look like a non-polynomial, but the idea is that we can have it mimic exactly if we can create a series that will go out to infinity. Okay. So the more information we give the polynomial, the more it's going to mimic and create a replica of the function that we're trying to imitate. And if we can create a polynomial version of a trig function, then it's a lot easier to do what we want to do in terms of finding the derivative, creating a model, and it's a lot easier to work with polynomials. So that's the benefit of these polynomials. Okay, all right, let's go to the next page. Let me go back to my screen. Hey, we're going to talk about how can we create these Taylor polynomials. How can we get? Well, right now it's going to be an approximation, because we're only going to work up to like maybe the third or fourth degree. So it's only going to match up to a certain point. But we will talk about some series that can go out to infinity and can match the graph exactly. Okay, so if f of x is a differentiable function, then an approximation of the f centered about the x can be modeled by. So this is where, if we can gather information from the function that we're trying to model, like sine or cosine of e to the x, if we can gather the order pair, the slope at a point, the concavity, the third, the fourth, the fifth derivative. So if we can start gathering information about each of the derivative values and inserting it into a polynomial, the polynomial will be able to have that enough information to start, creating a graph that matches the same property derivative-wise as the function that we're trying to imitate. So we're going to start off with basically tangent line equation. So it's got to share the same point as the function, and it's got to share the same slope at that point. So initially, it's just a first order approximation. You're just creating a tangent line equation. And then it's going to follow a specific pattern in matching the concavity, the third derivative value, the fourth derivative value. And what we're going to do is we're going to find the second derivative value of that function that we're trying to imitate and put it into this formula. And this formula will allow for that second derivative value to match once the two and the ones, once it gets down to a second derivative value, and we're able to find a constant. Okay. If we were trying to match it up to the third derivative, then it's f triple prime of c over 3 factorial. And if we want to match it up to the 10th derivative, 11th derivative, 14th derivative, we keep going until the nth derivative, evaluate at c, over n factorial times x minus c to the n. So however many degrees we want to go up to, we can find, if we want to get it up to the 14th degree polynomial, we'll find the 14th derivative match it up with that. And the more information we give it, the more this polynomial is going to begin to look like the graph that we're trying to imitate. Now, this is a Taylor polynomial where we can build our imitation from different x values. Could be x equals 2, could be x equals 3, could be x equals 5. But a Maclaurin polynomial is where we're beginning to match the graph that we want to imitate starting at 0. So Maclaurin polynomial is always building its case at 0. So the equation looks a little bit simpler because all the c's are just going to drop to be 0. So it's going to be f of 0 plus f prime of 0 x. It's still a tangent line equation, still y minus y sub 1 equals m times x minus x sub 1. But then after the tangent line equation, it's going to start looking like this form here. Okay, it looks a little bit cleaner because the 0 is going to wipe out the center. So let's do this. We're going to find a third degree Maclaurin polynomial for e to the 2x. So we would like to create a polynomial that's going to match this function's order pair, slope, concavity, and the third derivative value. So what we're going to do is let's gather all the information. We know Maclaurin polynomial means at x equals 0. So we're going to gather enough information, and then we can put it into a polynomial form. So our f of x is e to the 2x. Let's find f of 0. F of 0 is e to the 0, which is 1. So that's a y value that we want to use. F prime of x is e to the 2x times 2. And so f prime of 0 would just be 2e to the 0, which is 2. So at 0, the y value is 1. At 0, the slope of my exponential function is slope 2. F double prime of x, we just go through e to the u rule again. We get 4e to the 2x. Sorry, 4e to the 0 equals 4. Third derivative at x. So we have the y value at 0. We have the slope of the function of the curve at 0. We have the concavity value. We have the third derivative value. So we're going to put this into a Maclaurin polynomial. And it's going to basically look like one of the curves that I showed you from Desmos. It's going to have the first, second, and third derivative matched up. So it's going to look like that e to the x graph up to a certain point, but it's only doing a good job approximating up to that certain point. But let's build that Maclaurin polynomial. So f of x equals, let's call it p sub 3 of x. That just means that we're building a Taylor polynomial of a third degree. Okay? It's only matching the function that is trying to imitate up to the third degree. Equals to, basically, point slope form. So it's 1 plus 2x. So you're initially just always going to build your tangent line equation. And then after that, you're going to start following this formula. Okay. Plus f double prime of 0. So the f double prime of 0 is 4. So it's 4 over 2 factorial x squared. So it's a second derivative evaluated 0 over 2 factorial x squared. So all these numbers will match. Your derivative, your n factorial, and your exponent are all going to match once you start with 2. I don't follow that pattern with the first two terms. You could, but it just feels a little more awkward. It doesn't quite fit as nicely. So I just say, hey, just do a tangent line equation. and then build that form with the factorial and the exponent, starting with the second degree. And this is just going to be a tangent line. Next up, third degree, third derivative at 0 is 8. So 8 over 3 factorial x cubed. So this polynomial is going to match, it's going to have the same information as the e to the 2x in terms of its order pair, the slope, concavity, and the third derivative at 0. So if you can give it all that information, it's going to look like this e to the x graph up to a certain point. Obviously, we give it more degrees, it's going to match is going to become wider and wider. So it says evaluate f of 0.2 and p sub 3 0.2. So we just want to see, is this doing a good job of approximating a value close to 0? It should do a pretty good job. I mean, the tangent line is going to do a pretty good job already, but if it's curved all the way to x cubed, these two values should be pretty close, especially if we're close to the point of tangency. So just want to plug that in for you here. So if I want to find f of 0.2, plug 0.2 in for x, I get e to the 2 times 0.2, which is around 1.4198. And then p sub 3 of 0.2, I'm just going to save all the calculations on your end, 1.4906 repeating. So, right, pretty good. But obviously, this approximation can be even better if we were to add, a fourth degree match, a fifth degree match from our polynomial. All right, number 2. Now let's do a Taylor polynomial that's centered at x equals 1. So when it's centered at x equals 1, we just have to take the additional step of doing x minus 1. It's not going to be as clean as just x or x squared, x cubed. It's going to have this a little bit more messiness from the fact that we're not building the match starting at 0. We're building the match with the graph starting at a different center. But if we want to do a fourth degree Taylor polynomial, we need to get the fourth derivative of natural log of x, at least down to the fourth derivative, and actually find those values by hand. Okay, so let's take it one step at a time. Okay, let's just make our way down to the fourth derivative. Okay, so f prime, what's natural log of x's derivative? 1 over x, which is the same thing as x to the negative 1, because I can just get it ready for power rule after this. F double prime, negative 1x to the negative 2. Third derivative, 2x to the negative 3. Fourth derivative, negative 6x to the negative 4. Okay, so we want to find the value at 1 for all these function and derivatives. So let's do this. F of 1 is natural log of 1, which is 0. F prime of 1 is 1 over 1, which is 1. F double prime of 1 is negative 1 over 1 squared, which is negative 1. Third derivative is 2 over 1 cubed, which is 2. Fourth derivative is negative 6 over 1 to the fourth, which is negative 6. Okay, so we're going to create a fourth degree polynomial that is going to take the same information as natural logs, derivative all the way to the fourth derivative, and it's going to create a fourth degree Taylor polynomial graph that is mimicking this natural log graph up to the fourth derivative. So we'll do p sub 4 of x. And I just want to remind us that when you write your first few terms, it's basically just like it's like point slope form, right? Y sub 1 is equal to or y is equal to y sub 1 plus m times x minus x sub 1. So you're always going to start off by building a tangent line equation. And after you get that tangent line equation built, then you can start following the pattern of, second derivative over factorial x squared and building that particular formula. But I think it's easier to just not force this formula onto the first two terms because it is just a tangent line equation. Okay. So my y sub 1 is going to be 0 plus my slope times x minus 1 because that's my center, centered at 1, x minus c. All right, from here, the pattern will begin to be more, will be the same. So we're going to use the second derivative. So -1, that's my second derivative at 1 over 2 factorial times x minus 1 squared. So second derivative, 2 factorial, raised to the second power. So now all the numbers will begin to match. Plus third derivative, evaluate at 1. So it's 2 over 3 factorial, x minus 1 cubed. Next up, fourth derivative. So fourth derivative, evaluate at 1 is 4. Sorry, -6. Okay, so we're just taking information from the natural log function and taking those information and sticking it into the polynomial so that it can share the same values up to the fourth derivative. And then it says evaluate f of 1.1 and versus the polynomial at 1.1. And you can see that it's doing a pretty good job. First off, it's close to the point of tangency, and we have it all the way up to the fourth degree. So the actual value of the function at 1.1 is very close to the polynomial approximation at 1.1. All right, let me just do one more here, page 9. So when we have the Taylor polynomial, it's going to take on this form of nth derivative evaluated at c over n factorial times x minus c to the n, right? If we're talking about the fourth degree, then my n is 4. I need to do the fourth derivative. I want to match it all the way to the sixth degree, then I need to get to the sixth derivative. Now, a coefficient would be this value in front of the x. So when it asks for coefficient, it's asking for what is this number going to be? That's the coefficient of this Taylor polynomial at this degree. So number 3, it says let the function with the third derivative being here. So this is taking us all the way to the third derivative. What is the coefficient of x minus 2 to the fourth? So I have the third derivative. I want to get to the coefficient involving this to the fourth. So I'm basically trying to do this. I'm trying to find the fourth derivative evaluated at 2 over 4 factorial x minus 2 to the fourth. This is what my fourth degree term will look like, but it's asking for the coefficient. So I'm trying to get to this value here. Well, 4 factorial, that we already know what that is, but the the fourth derivative evaluated at 2, we just have to make our way down to what? We have the third derivative, so how do we get here?
Just take the
Yeah,
derivative.
take derivative once and then plug in 2, yeah. And then once you find the fourth derivative at 2, then that can plug in for this. And then this divided by 4 factorial would be the coefficient of this term. So here's the fourth derivative. We just go through chain rule. 8x plus 2 to the 3 halves becomes 3 halves 8x plus 2 to the 1 half times 8. Outside derivative times inside derivative. I'm just doing a little bit of cleanup. Then I plug in the 2. And I don't have to clean it up all the way to this point. I just wanted to make it easier for me to, if it's a multiple choice question, I want to be able to get it down to that form. So I get 18, square root of 18 is the same thing as 9 times 2 inside the radical. I can pull a 3 out. So 36 root 2. That would be the numerator of my coefficient. But my coefficient also includes that 4 factorial. 4 factorial is 4 times 3 times 2 times 1. So 36 divided by 12 is 3. And then 3 and 2 will remain, so it's 3 root 2 over 2. And I'm not including the x minus 2 to the fourth because it's asking for the coefficient. So it's only asking for this portion that I've boxed off in red. All right, if we can go to our worksheet 3 and continue working, let's see if we can do 10 minutes, see if we can make some progress there. I can walk around, see if you have any questions. Okay, and it's going to be a test tomorrow with a calculator covering those topics from worksheets 1 through 3.
Right, just put up there.
Yes, yeah. After 3, we start using numbers.
Okay.
Yeah.
Like, I mean, it was, see, it was as easy or hard as, the one before. However, that